Okay, folks, we're going to take a look at 7.3 probability distributions for continuous uniform random variables. The section in the book focuses on continuous random variables in general, definitely good to read. In terms of the math, we're going to focus on the uniform distributions. But let's take a minute to talk about what a continuous random variable is, okay? A continuous random variable is one that has possible values that form an entire interval along a number line. Often these variables are thought of as things we measure. Common types include, but are not limited to, time, volume, weight, area, length, height, things along those lines. Continuous random variables can, in theory, take on any value, no matter how obscure, like some fraction of a number, like that could be 20 or so decimal digits long, or some irrational value, like maybe the length is 2 radical 2 miles, or the volume is pi cubic units, or something like that, okay? They can take on any value along a number line, okay? Including weird, obscure decimal fraction of a value, okay? But in terms of being able to measure these things, they can only be measured to the accuracy of the measurement tool. For example, in the Olympics, timed races are measured to the nearest hundredth of a second. While that's impressive, if better technology existed, a more accurate tool might read to the nearest thousandth or even a millionth of a second. And in theory, we could perhaps measure to an even smaller fraction of a second. But is there a smallest unit of time? Okay. The answer is, well, in theory, no, there's not. Okay, what does that have to do with the graphs of these things? Well, the graph of a continuous random variable forms a smooth curve. Okay, unlike with discrete data, which can be graphed as histograms, continuous data tends to form curves. It's continuous. It's not blocky. It's smooth. Okay, a histogram might look something like this, whereas for discrete data, whereas for continuous data, we might get a shape that looks more like this because we're measuring it tiny, tiny intervals of time versus over groups of intervals, okay? So really, all you got to really know about this is if we're dealing with continuous data, we get a graph that forms a smooth curve, okay? The two types of continuous random variables that we look at probabilities with the most in this course are uniform distributions and normal distributions. Okay. Here's what the general shape of a uniform distribution will look like. That's it. It is just a horizontal line on some interval over which we're working. In a normal distribution, which we've seen before, has this general shape. Okay. Now, we're going to cover normal distributions in another lesson, and if you think about it, we already know quite a bit about these from Chapter 4. This lesson, the examples will focus on uniform distributions, okay? So, a uniform distribution is a continuous random variable where the chance of occurrence is equally likely for all possible x values along the interval AB, okay? So, looking at our graph, we have some chance of occurrence that's equally likely between these two values. We have a horizontal line, okay? Now that's going to have some constant y value there, and that is called the density, okay? Well, the idea is this, just like with a normal distribution curve, the area under the curve gives us the percentage of data that lie within regions of the curve, okay? So the total area under the normal distribution curve is 100%, or adds up to 1.00. Same thing is going to be true with the area under the density curve here for the uniform distribution. Okay, and it's going to be true really for any sort of curve that models the percentage of data. The area is always going to be 1 equal to 1, representing 100% of the possible outcomes. Okay, so if you think about what we really have here in terms of our density curve, okay, we're going to be able to compute that y value that we're calling the density right there. Okay, and here's the idea. We can cut this curve off at A and B. And what have we really just created? A rectangle, okay? And what do we know about the rectangle? Well, the area under that thing is exactly equal to 1, okay? Always representing 100% of the data, okay? So how do we find area of a rectangle? Well, area of a rectangle is base times height. We know the area is 1. We can actually compute the length of that base, and this y value that we're after represents the height of this rectangle, okay? So how do I represent the base of this thing, okay? Well, look, suppose B is at 10 and A is at 3. What would the length of the base of that rectangle be? It would be 10 minus 3 is 7, right? Or if B is at, say, 20, and A is at 15, what would the length of the base be? Well, it'd be 5, right? And how'd you do that? 20 minus 15. In general, the length of the base is given by B minus A. You're just subtracting those values. So I'm going to replace that with B minus A. So in any event, the area is 1. The length of the base of the rectangle is B minus A, and the height of the rectangle is Y. So we get this little equation, and if we want to solve for Y, what do we have to do? I'll just divide by B minus A. And this gives us that density, that Y value on the graph, okay? So the constant Y value representing the height of the rectangle is called the density, and it is found by Y equals 1 over B minus A. Or if you want, you can use the letter D for density, whatever, okay? But it represents the height of the rectangle, okay? And so what we do is and we'll be told in a problem, we'll be told if something is a normal distribution, as you'll see in the examples. And so basically what our job is to do is to take what we're being given, sketch the graph of this thing, and then we're going to look at areas of certain regions under the graph between whatever values we're told to find the probability of occurrence. So let's take a look at how this stuff works. All right. The wait time for the bus forms a uniform distribution on the interval 0 to 20 minutes. Okay, so we're talking about a continuous variable, wait time, and it forms a uniform distribution on the interval 0 to 20 minutes. What that means is you have an equally likely chance of waiting anywhere from 0 to 20 minutes to catch that bus. If you're running right up when the bus is there, you're waiting 0 minutes. If you get there right after the bus leaves, you're going to be waiting another 20 minutes for the next bus to come. So you could wait any amount of time from 0 to 20 minutes with an equally likely distribution. Let X represent the amount of time a randomly selected person who takes the bus had to wait. Determine the following probabilities. Okay, what's the probability they wait less than this, more than that? Okay, first thing we're going to do is sketch the graph. Okay, so I'm going to make a y-axis and an x-axis. X is the wait time, and it's on the interval from 0 to 20 minutes. So I'm going to make that go from 0 to 20. So my graph is just going to be a horizontal line over that interval, and I cut it off at 20. All right, and what we need to do is we need to figure out what the density is. Okay, so again, the density, or that y value, is just 1 divided by b minus a. Well, here a is 0 and b is 20. So 1 over 20 minus 0, 1 over 20 it is. Okay, and you can leave it like that. You can use 0.05. It's, however you want to use that number is up to you. But now, given that we figured out what that height was, right, we can come up with these probabilities. So let's take a look. What's the probability that we randomly select someone who waits less than 10 minutes? So I'm going to write it like this. Probability X is less than 10. So what we do is we come over to the graph, and I'm going to highlight where 10 is. And if I want to wait less than 10 minutes, I'm going to shade this thing to the left. And what I'm now going to do is I'm going to find the area of that rectangle that I've just drawn. And the area of that rectangle will give us the probability that we seek. Okay, so again, all we're doing is area rectangles to come up with probabilities here. Base times height. From 0 to 10, that's a base of 10. And the height we know is that 1 over 20. So here we're going to get 10 over 20, or 1/2, or 0.5, or a 50% chance. Okay, there's a 50% chance that this person's going to wait less than 10 minutes for the bus. Let's take a look at part B. Okay, so you can either redraw the diagram or you can erase like I have. In part B, what's the probability they wait more than 15 minutes? So I'm going to write that the probability that x is greater than 15. So again, I'm going to come to my diagram, eyeball where I think 15 is, greater than, wait more than 15, I'm shading to the right this time. And now I'm looking for the area of that green rectangle. So again, base times height. The base from 5 to 20 is 5, and the height is 1 over 20. So I get 5 over 20 back, 1 over 4, or 0.25. There's a 25% chance that this person will wait more than 15 minutes. Now let's compare that to part C. What's the probability they wait greater than or equal to 15 minutes? So the only difference in the notation from part B is that x is now going to be greater than or equal to 15. Here's where this is going to be a little bit different than what it was with discrete data. When we have our probability distributions in our tables for discrete data, when we include a value like greater than or equal to 15 versus strictly greater than 15, those numbers are typically different. This is different now for continuous data, okay? It's actually going to be the same exact answer we got in part B. There's no difference as to whether or not we include the 15. I'm going to draw the line at 15 just like I did in part B. I'm going to shade to the right, and I'm still going to find that area. The length and the base and the height of this rectangle has not changed simply by including that one value, okay? So it ends up being the same exact thing. The base is 5, the height is 1 over 20, and we're going to get back the same 0.25 that we got in part B, okay? So what does that then tell us, looking at part D? What's the probability they wait exactly 15 minutes, okay? Well, again, the way we compute probabilities for continuous data is we look at the percentage of data that lies under that section of the curve. If I go to the graph and I draw a line at just 15, I'm not going to shade to the left and I'm not going to shade to the right here. I just have a line at 15. Well, if you think about that as a rectangle, what's the base of that rectangle? What's 15 to 15 a length of? Well, that's a length of 0. And the height is still 1 over 20, but what's 0 times anything? 0. Okay? This is a big difference between, again, discrete and continuous data. The probability that something weights exactly one value under continuous data always equals 0, because you think of this as a rectangle with 0 width, and if the width is 0, the area is 0. And that's how we calculate the probability. So it might seem like a little bit of an abstract idea, but in reality, if we had a stopwatch that measured to the nearest nanosecond, we probably would never ever hit exactly 15 seconds on the nose. It would probably have some variation, some fraction of variation of a second. Okay, so again, watch out for these with continuous data. It's going to be 0. If we're not shading one way or the other, we've got a rectangle with 0 area. Okay, let's take a look at part C now. Here, what's the probability they wait between 6 and 12? So I'm going to write this probability x is between 6 and 12. And again, same idea. Here's where I think 6 is. Here's where I think 12 is. I'm looking for the area of that blue rectangle. 6 to 12 is a base of 6. And again, the height is 1 over 20, so we get 6 over 20, or 0.3, or 30%. Okay, 30% of the time we'd be waiting between 6 and 12 minutes for that bus. And what's the probability they wait exactly 19 minutes? Well, again, that's a lot like part D. Okay, the probability, it's exactly 19. Well, I can draw the line at 19, but again, it's got no width, it's got no area, so the probability is 0. What's the probability they wait more than 19 minutes? Now I've got some area. I can shade to the right. The base of that is relatively thin. It's just 1 as we go from 19 to 20. And so we get 1 over 20, or a 5% chance. 5% of the time we're waiting more than 19 minutes. Okay. And part H, what is the expected or average wait time? Okay. Well, the expected value or average is really just the value that's right in the middle of our original interval. Okay. And so how do we find the average of that? two numbers we're going to add and divide by b. So the expected value here is given by a plus b over 2, which ends up being 10 minutes. Okay, in general, we would expect to wait 10 minutes. Half the time we'd wait less than that, half the time we'd wait more. Okay, and this is the gist of these types of questions. As you'll see in the next example, again, I use wait time as our uniform distribution. So let's again see how these play out. The wait time to be called at the doctor's office forms a uniform distribution on the interval 5 to 45 minutes. So that means you've checked in, you know you're going to be waiting at least 5 minutes before they call you in to be seen, and you may wait up to 45 minutes, depending on how busy they are, or anywhere in between with equally likely probabilities. Okay, so before we even start looking at the questions, let's go ahead and sketch this graph, this density curve. And again, it's called a curve even though it's a straight line. But here we're on the interval 5 to 45 for minutes for x. Label this the density. And we're going to want that height. Okay, so there's the graph on the interval, horizontal line. And again, the density is just 1 over b minus a. 1 divided by the length of the interval. In this case, we get 1 over 40. Okay. All right, so now let's compute some probabilities. What's the probability they waited more than 15 minutes? The probability x is greater than 15 here. So okay, so I'll draw where I think 15 is, and I'm going to shade to the right. And so now we're looking at the area of that rectangle. Base from 15 to 45 is 30 times 1 over 40 for the height. So we get 30 over 40. You can certainly leave it like that. You can simplify 0.75. Okay, 75% of the time we'd expect to wait more than 15 minutes. Okay, what's the probability they wait exactly 15 minutes? So again, that's going to be 0. We get a rectangle with 0 width, 0 area. What is the probability they waited less than or equal to 15 minutes? So this time we're shading to the left. What's the base of that rectangle from 5 to 15? 10. And so we get 10 over 40, 1/4, or 25% of the time. And what is the expected wait time? So average value, a plus b over 2. 5 plus 45 is 50 over 2. And basically what we're finding is the average or median wait time. Half the time we'd wait 25 minutes or less, half the time 25 minutes or more. Okay, so get used to sketching these graphs. If you have any questions, shoot me an email. Take care.